Okay, so this is for an AND gate. So let's do for an OR gate. The same idea, right? So for an OR gate, A, B. So if A is zero and B is zero, what happens here? You guys know you guys know this one already. So if A is one and B is what is it? Any other answer? So zero, why? X and zero is why X? Hey, Charlie, nowadays you guys are picking up. Yeah, that's the X. You said what zero, right? So why? So so it's an okay. So one one of the input is zero, right? The output here will depend on this. If A is one, it will be one. If A is zero, it will be zero, right? So now we have A to the X. What will it be? X. So okay, now they say if here is Z, what is it? Don't say Z. I just knew that's where you were going. But I've explained. So if here is Z, what is it? Why? Masa. Now, I said if the output of all the gates, right, can never be a Z. So if one of the inputs is a Z, that means that here will be an unknown, not a Z. Understood? Do you understand? Masa? Understood? So for the okay, so now you guys know what so if yes, X, yes, X, plus the X, 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 Z. So you see how easy that is. Understood? Yes. So in the exam, I gave an AND gate, right? So I might bring an OR gate or a NAND gate or something. Okay, so we have gone through all the syntax for I think for Verilog also. So here, how do we convert our code to the gate? As I said, if you want to write your code, your model, you want to write your model, whatever, and gate or whatever, then and model. This code has to be changed into gates, right? And then I think, and I've said that they're using a tool called Verilog, right, to convert these models into gates for us, right? Those are the tools. And I hope by now everybody has installed the tool. At least you guys have all installed it, right? Because the next time you'll be doing the labs with the tool. So if you have not installed it, and if not a machine, then I don't know how you partake in the lab and get some marks for the lab. I hope you guys all have laptops and stuff. Or you guys have a lab here, a computer lab, right? So it is large enough for everybody to enter. Are you guys doing? So how are we going to do the labs? Okay, so now we convert our models into logic gates using, somebody has said that I am giving free marks, right? Somebody has sent the information that I'm giving free marks, right? Who sent the information that I'm giving free marks? Nice. So we can convert our codes using our software tool, right? And then I think I said that after you've converted the code, your next stage is to manufacture the chip, but you have to do some simulation to see whether it works or not. The tool will also enable you to do that simulation. And then you must know that designing the model and testing, the time it takes to test the model is more than the time it takes to actually design. You spend about 30% of your time designing and about 70% of your time in trying to test. So, so the testing is also very, very important, right? You can read this, and just some advice on hardware coding, right? Okay, now we can also define our own gates in Verilog. We saw that I think I said that in Verilog we have some fixed gates like the not, the and, or X or I think that's it. These four gates are fixed, right? So it means that if you want probably not X or something, you have to design it yourself, and it's just easy, right? So here, and I want to design. I think we have seen this one already. The 4 bit comparator. We have seen it already, right? We have A, B, 4 bits. We want to compare those two numbers or those two values. If A is equal to B, then the here will be what? What will be the output if A is equal to B? 3 marks, 3 marks. What's your name? Just 3 marks. So Collins. Master, I can see your name here. Collins. Cornelius. Yes, 1 mark free. So now, if A is equal to B, the output, or here you see that here is 1 bit, right? The output is a 1, right? What if A is not equal to B? So if A is not equal to B, the output is 0. So how do we design this using our own gates? Our own gates, right? So I can just do that with that code over there. Model my XOR, XNOR, right? And then you can see that the XNOR is what? It's not X, not XOR, right? So I can have A or A, X or B, and then once I put the notes here, that's just an XNOR. You see how that easy? You see how easy that is, right? So here I just assign z is equals to not a x or b. Then I've designed my x norm with inputs a, b, z. Master, look on the code, though, right? Understood? Understood? Okay, now after you see here, it is actually made about x norm and an AND gate, right? I can also design an AND gate, but an AND gate already exists. But I can still design my own AND gate to model my AND gate and input A, B, Z, then Z is equal to A and B. Simple, right? So now I'm going to combine these two, the X norm and then the AND gate, to design this whole thing. Understood? So just look on the board and see. So this is what we're about to do. Right. So now I can first of all start by defining my model compare the inputs A0, A1, A2, A3, A4. Input A0 to A3, then input B0 to B3, then output equal or whatever. Right? Then I'll have some wires inside the wires, right? I'll have wires inside there. C0 probably is C0, C1, C2, C3, right? And then C01 and C23. Now you must understand that we designed an AND gate here, but once you look at the code for the AND gate, it's just 2 bits. A is it's just 1 bit AND gate. A is 1 bit, B is 1 bit. But you see that here, this AND gate here four has 4 inputs. So how do we address this? Who knows? I have 4 input and gate here, but I only have but the AND gate I have has only 2 inputs like this, right? So how do I do it? Charlie Paul Maxwell.
We take two of the input, then we separate the inputs, the wires of the two. So these two and the pass to another one.
So how will it look? How will it look like? I mean, the drawing for that.
So the first wires of the candidate. So and the other two people are candidates. So the other
Right? This also looks here. So that's right. Another point. Free. Right. So basically, what you do is that what you can do is that maybe you combine these two with one AND gate. So if this and this will be one AND gate, and then the output of this one will be fed into another AND gate, and then we give this one here, right? So this is 3, right? And then the output of this one too will be fed into another AND gate, and then we give this one here. So you see that you have 4 of them, 4 inputs. Understood? Understood? That's why we have C01 and C23 as wires, right? So here, what I'll do is that now we have 4 x what? Not all x no gauge, right? 1, 2, 3, 4. So they are all here. 1, 2, 3, 4. And then we name them I0 to I3. That easy, right? And then you can see that we connect. You guys understand? I told you what if I do dot A into bracket A0 means, right? What does it mean?
it means the user is connected to
It means that I have a model here. You see, my X now has input A, right? So I that is for the dot A, and then I have A here as input, right? I just connect it to the dot A, and then understood. Is that easy, right? Do you guys understand? Okay, so that is how it looks like. And then I have three AND gates. For this three AND gates, one, two, three. Understood? Do you guys understand? If you don't understand, just say it. Or you don't know what you don't understand. You know, do you guys understand? Go through it, go through it. First of all, I said I am designing this, right? With my own gates. So I first of all said we are going to design these two models, my X no and then my AND gate, to use that one to actually make this gate please, right? And then I come here and I declare a top model, and then I call this my X no and then my AND gate within it, and just give it those the inputs and the wires. It's actually that easy. Once you guys understand, where or what don't you understand? Please hurry up and let's continue. If you don't understand anything, what? You don't understand. Who doesn't understand? Should we continue? Should we continue? If you don't, just say it and let's. What don't you understand? Or like, I should write it down. Like, I should write on the board before you understand. Because you're going through all of that, how to actually design a model, how to call a model. You guys already know that. I've already thought that. So I thought this was going to be easy. Pardon? Yeah, I said that for this one, this AND gate here is all input, but my AND gate I'm using is only two inputs. So I can break it down to be something like this, right? So C, probably C0, C1, C2, C3 will come inside here, and then the one will be C20, C01, and then you see that the one, this is an internal wire, so I need to declare it like C01 or whatever name I give it, and then there's another wire also, so C23 or whatever it is. Understood? So I have actually taken this circuit here and kept it here. Understood?
I'm getting confused at the set the I'm getting confused.
Why did you?
You are doing X now for the first bit, the first one for the first
Yes, sir.
the first one. So you have the three is the first one.
Okay,
I
so
don't know the next.
that will be for this one.
Yeah,
Okay.
the Z is zero.
Yeah.
So when you
Internal wire C0. So it has to write it down for
the
you.
other side, when you give my X one, we assign the X one to six,
Yes.
and then the
So then my X1 is A, B, Z. Right? So yeah. So yeah, the dot Z is that X0. Dot Z, then I assign C0 to it. Understood? Or let me bring all those codes over there. Where am I? Okay, wait. Okay, so you see that here is my what X number, right? And this is my hand. I have to first of all define these two in the file. This one is already there. This one is already there. So here, all I'm doing is I'm just calling these ones, and I call them X1, and then I have four of them here. One, two, three, four, right? I call my first one X01 dot A. You see that the dot A is for this one. Dot A is like A0 for the inputs, right? As you can see, like A0 here is connected to dot A of this model, right? So, and I do that for the four of them. Then I come to the answer. We have three of them because actually I made this one into three of them, right? So I have three of them here, and I just do my connections. Is that it? Shall I continue? Okay. So this is structural modeling. As I said about, I said that we have two types of modeling, right? I think I mentioned it. Structural, then what? Yeah. All right. So this is structural modeling, and then I said that for the structural modeling, it is actually very, very tedious to do, right? That's why you guys are actually getting confused. So now you see that here I can replace the AND gate I made with just this one, the AND gate, right? And understood. I have actually replaced this AND gates. This my AND with this one. I replaced all the three of them. Can you guys see?
Yes.
So I have C0 and C1 is equal to C0 and C2 and C3 is equal to C23. Then C01 and C23 is equal to the output there. It's assigned to the output. Understood? Now I can actually also replace these three codes here with only one statement, right? C0 and C1 and C2 and C3. That easy, right? Are you guys seeing how it's been done? So it means that I can write long codes or short codes. Understood? Then I can replace C0, C1, C2, C3 with here we have three ands, right? I can just replace that with only one and gate and C, and then I'm done.
So over one thing.
I have
Yeah.
equal, right? It's equal to C what? 0 and C1 and C2 and C3, right? I can just replace this with only one AND gate. And then you guys know how to do that. We talked about the reduction operator. If you go to your slides, you see it unless you have not gone to your slide. I talked about the reduction operator. I can have AND here, and then maybe and have C to be 4 bits. declare C to be 4 bits, and then I take the AND of C, right? And then it will go to this does the same thing as this. Understood?
Yes.
I understood. Okay, and then if you write, if somebody does something like this, and this and C, and somebody does a thing like this, and then or the person does assign all of this, right? They're all actually the same, but it's just that this makes your code shorter, right?
What is very different?
So how will you draw? Okay, now so how will you draw this one?
Like this.
I mean, just for this and just and C means what?
It will be like this one.
Yeah, it will be it will be the same, exactly the same. And I didn't explain the last time. If you have if C is 4 bits, right? If C is like 4 bits, and then I have something like and C, right? It just means I have something like this. C0, C1 connected to another and C012 connected to another and C3, right? It's just the same. It's just that I've made my pose shorter or something like that. Understood? Okay, so I can actually shorten that one. Then you see that this is my x1, x1, x1. I can replace all of them with just one statement, right? This A x of B, then not C. Understood, right? I can replace all of this one. I can design all of this one with just one statement. And then that C is equal to that boolean. Yes. You guys know that, right? It's that easy, right? So how do I translate this code into this? It is essentially the same. C is equals to, and then remember that C is 4 bits, right? And C is equals to not A is 4 bits and B2 is 4 bits. This equation is the same as this for XNOR gates. No, are they the same or not? Do you guys understand?
So, but in that case,
Mhm.
the because the function is related to the extension, you have to like take the value from the small bit to pass to the US
But
value.
now we are no longer trying to do that. Once I say assign C is equal to we have just ignored all those ones. I'm just going to make a point that your codes can be actually so many, or your codes can be shorter, right? And and then all of them are actually basically the same. Understood? No, basically the same. Okay, shall I continue? Now I can even still make this one shorter.
And that's why
So it means that I can still make it shorter, right? By just having only one statement equals A is is going to be. You guys know what this. You guys know the conditional operator. Understood? This also works the same way. Very, very easy, right? Or I'll make it so if A is equal to B, what happens? One will be assigned to. Else, if A is not equal to B, zero will be assigned to. That easy. And then that this is just a 4-bit comparator. Understood? Now, understood? Good. With 4 variables. No, no, no. I mean, this is hardware. The hardware, all the codes run in parallel. It's not software. So this is not like your software code where you run in parallel, right? Hey, where you run one line at a time. All the codes are actually implemented as gates itself, so they run at the same time, right? So that's what it does. They just at the exact same time. So as I said, this is almost the same as it, or it does the same way, right? But do you guys understand? Before I make a point here, do you guys understand? Massa.
This one.
Yeah. Understood, right? So now let's let's check something here. Once you're writing once you're writing hardware codes, right? Like this, right? Somebody I think if you're writing in C, like in case you're writing your codes in C and then somebody uses let's say one line of code to do to do something to do something that is done by about 10 lines, right? That person is a good software engineer, right? So if you use like one line of code to do so much work, that is a very good engineer, right? But here the hardware, it depends. If somebody writes one line of code, right, to do so much work or to do so much, right, that person might use more gates, and that will cost you more money because the more the gates, the more you pay. For instance, if somebody did it with only gates, right, then like it will look like this. Now, if somebody does it like this one works the same as this, right? But what happens here? Now it means that instead of using X, instead of using probably um, an XO gate and not XO gate, not XO gate, not XO gate, not, and then an AND gate. What the person has done here is that the person has created a multiplexer because it selects from two inputs, right? The person has done now 1 and 0 will be assigned to this based on what A is supposed to be, right? Understood? This is what the person has done. Now this A is equivalent to B here is the same as this. So what the person has actually done is that the the person has actually used this one here. Then the person has extra gates here. That's what the person has actually done, right? So if somebody writes so long code like this, right? This one uses less gates than the person who writes only this one line of code. Understood? So in hardware, um, your your design must be as close to the gates as possible. You design with the gates as much as possible. You design so that it is so close to the gate. Once you write a very high level language, once you write a very high level something like this, it's going to need more gates, right? And
Like I said, the code must look like the design.
yes,
It must be as complex as possible.
yes. But in that case, it means that you are using more time to do that. So now, so it depends. So you will use more time to design to actually design, but the cost is less. Or you use a very short time in your design, and then your cost is more. So you choose one.
What are processing time? Do we affect processing?
Nah, it will be the same. It will be almost the same.
So, what about academically?
Hmm?
Should you, academically speaking,
Pardon?
academically speaking,
Eh,
should you do the long one or you can represent it with the short?
they're all the same. Once it does the function you have to execute.
So, if I'm not building, I'm just using the theoretical
And you can use any of it. It's the same one. It's the same one, but in the industry, it's different. If you go and write something like this in the industry, they'll be annoying with you because you're costing them money. Understood? So I continue. So now we looked at, let's say, designing a 4-bit comparator, right? What if I want to design, I want to always change this. Maybe today I want a 4-bit comparator. The next day I want 5 bits, 6 bits, 7 bits. So how do I design that? Anybody?
So you think if you have a form
You
before,
see that once I declare my model, right? Once I declare my model, probably compare A, B, Y. I always come and say inputs 3 is to 0. A, B, probably output Y, right? So this one means that I can only do 4 bits comparison. Every time A must be 4 bits. Once I go beyond 4 bits, there will be an issue. So, quite if I want to design my model in a way that it can take so many bits, it can take 4 bits or 5 bits, 6 bits, 32 bits, 100 bits, 200 bits, right?
is there a way to make these numbers variables?
Yeah. So means that here our main issue is that we fix numbers here. So we have to change that. You see that here is always 3. So why is it always 3? Why can't it be, for instance, the width? So that once I'm calling it, I give it a width, the width I want. Understood? So we do that with parameters in Verilog, right? So here, if I have like a very very simple multiplexer, it takes when it takes so now if you see any code, right, any Verilog code, you should be able in your mind to draw how it looks like. Right now, I know that once you see a code like this, y is equal to s, and then s d1 d0. You guys can draw the circuit, right? Pardon? If you see something like this,
If S is true, then assign D1 to Y,
well,
S to Y.
so what gate is what
This
combinational logic is this?
this is
I've done this so many times, but
yes,
is that what? A multiplexer, right? Wait, how many inputs? So once I see something like this, and I just know that it is amongst 2 inputs, my output is what? Y. I have one of the inputs to be D1. I have one of the inputs to be D0. I have the select, and then if select is 1, is D1, right? So I come and put the 1 here. If select is 0, is D0. I put the 0 here. Once I say a code like this, this is what it will translate to. You must know this offhand. It's just that easy, right? So now here, instead of giving it instead of giving the model fixed, instead of making here um, D1 and D0 to be, let's say we either do 3 is to 0 or 4 is to 0. What I do is that I make my thread a variable, not 3 anymore, but it will be 0 is to the width minus 1. Understood?
Yes, sir.
So here, in case I'm designing the model, I first of all start with the hash, the interrogative parameter. Then I declare my width. First of all, right? So here I can declare any width at all. 8 bits, 4 bits, 5 bits, whatever. But you declare your width first. And then you come input width minus 1, 0, D0, D1. Then output width minus 0, width minus 1, 0. Understood? Do you guys understand? Hmm? Yeah, so I said instead of doing having a fixed bits for the D0, D1, and then the output, right? I can use variables inside there. So wave minus 0, wave minus 1 is to 0. And then what this means is that anytime I give it a value here, I'm giving it parameter width is equal to 8. It will be what? 8 minus 1. And 8 minus 1 is what? 7. So it will be something like 7 is to 0. Understood? This is easy. Right? So now,
From the S is 1 bit, or the S 1 bit.
yeah, the S is just one. Because we are just selecting two of them. This one and D1. If in case there were more, then the S will increase. Right? If there are three, we call it 3 marks.
If they have like three,
Then just write the rule. 3 marks, so just write the first person. Then Suleiman in the first name. Last name of it. Suleiman. The first last name is what? Ah,
let's say we
I can't hear you. Far. Your name is not in the class list. So understood. Okay, again, if I have D0 to D31, what will be this? Another 3 minus 1. So I have D0, this is my motor lecture, up to D31. What is this?
5 bits. 5 bits.
Pardon? So, so this is the parameter. Okay, so now here, I can call it anytime I want, right? So now here, you 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 must actually fix it within that model, the model X. Right here is model what? Mux 2, right? The most important thing is that I have the parameter must have a fixed value. Okay. Right? If I first of all have a fixed value, right? Why? Anybody?
Because when they want to change it to any other, you
No,
just
no,
do
no,
it.
no.
What's the question?
I said declare something like this. Model mux 2, then parameter which is equal to 8. I think in case you are doing, let's say, probably C or something, right? You won't actually specify it to be a fixed something. You will just say wait for something, right? Only wait, and just assign it any number you want, right? Later on, but here every time it must be fixed first. It must be fixed to 8, so that if somebody or if in case you call it without giving it a value, it will be 8. Understood? Because I have to call it from some higher model, right? A higher model called this one, and then assign it values, just like in C, right? Function call, like main, you call a function, right? It's the same thing. So here I can actually design another model that will say, oh, I'm using 12 bits. So that model will assign that 12 bits to this one. But first of all, here it must always be fixed.
So the age here looks like a default value.
Yeah, a default value. Yeah. Have you understand it? If you don't understand, as I said, it is actually you can get 0 or 100%. As I said, there's no middle ground zero. 0 or 100. It's 0 or 100. There's no middle ground. So right, so it must be fixed all the time. Right. So now if I want to call it, how do I do it? Now I have to design another model, a top model that will call it like my main, it's main or something. And then the main will actually call this one. But here we are using the same model. So if I want to design probably if I want to compare this 100 big numbers, 100 bits, 100 big, 100 big numbers, right? I just do like model 100 or something. But 100 compare or whatever. Then I give it inputs A, B, and then I give it what my Y, right? Then I come and say inputs 99 is to 0 is 100, right? A, B, output Y. Understood? Then from here, I now call it it's what? Mux 2, right? And I give it any name I want. Mux or whatever, whatever. Then I do hash, give it 100. And are you understanding? I'm giving it 100 here. Then, and I'll do the dot, whatever, whatever. Dot what? So here it will be what? Dot what?
So explain the 100 first.
So here, okay. This is the model, right? Mux 2. And then the Mux 2 has a fixed width of 8. As I said, the parameter 8. Now, I want to design another model that will call this Mux 2. But now, I want to compare 100 bit numbers. Just the same as them. It's the same, but here, I'm not comparing 100 bit numbers. They're just one bit. Oh, okay. This is not a comparison. So sorry. This is not a comparison. So gate is 100 bit, right? 99 is 0, right. So I've designed this, right, and I want to call this one in my main function or whatever. So it will be model, let's say 100 or something. A, B, C, input 99 is to 0. 0 means this is 100 bits. 99 0, A, B, output 99 0, Y, right? Then I call it mux2. This is the mux2 I'm calling, right? Once I call it without giving it, once I call it without giving it any number here, right? It will still use the 8 bit. So if I want to assign my 100 bits here, I just have to call it and do hash bracket 100, right? So what it does is that once it calls the code, it usually replace the with 8 here with 100. That's all it does. Do, do we understand? So now here 100 then into bracket dot what? So dot d0 or something into bracket a comma dot d1 into bracket e then dot what? Dot what? Into bracket here. Here is what? Simple. Do you understand? Understood? So this is an easy way of so if you go somewhere anywhere in case you are designing, if they say, for instance, design a 4-bit adder, right? To make your way easier because the next time they will come and tell you that, oh, we don't want 4-bit adder anymore, we want 8-bit adder or we want 32-bit adder. So anytime use parameters and instead of designing just the 4-bit adder, use parameter here like this. And then declare something like your width or something. And then anytime you can easily change it to whatever bits you want without going to redesign the whole thing again. Any question? Yeah, yeah, yeah. Are you understanding? Okay. So so now everything you've done is combinational logic, right? Everything we've done so far for the coding side, everything we've done is for combinational logic. We know, and then that I think I started with combinational logic before I went to another one, sequential logic, right? So everything you have done is for combinational logic. But how do we design for sequential logic, right? And then the combinational logic always use assign, the assign statement, right? Assign something y is equals to a plus b or whatever. Once I use this, it's combinational logic. You know why it is combinational logic? 3 marks, 3 marks. Combinational logic. If I use a statement like this, assign y is equals to a plus b, this is just what? Addition, right? Add a to b, and then give the results to y. And I'm saying that this is combinational logic. Combinational logic. We have already treated what combinational logic are. The gates, encoder, decoder, all those things are combinational logic. Why are they combinational logic? I've said this one before also.
That's
3 marks, oh, yeah, just 3 1 mark, then you have to find 99% or something. We have, I think somebody is reading the thing. We get answer right. We have two types of logics in digital systems, and I've already done that already.
Then we also have states.
Huh?
Then have states.
Answer. We have combinational logic, and then we have sequential logic. And I explain why they are called combinational logic, and I explain why the others are called sequential logic. You've done this already. Hi. So how many times do you guys go through the slides or something? You guys have never gone through the slides, right? Anytime I teach students, they just
Special logic was the one that one was bitwise. And the one has states. Like one has states. The combination doesn't have states.
pardon? Uh-huh. They used to do what? Complicated. So I wish my time for so no one. How many people here? About 30 people. Nobody remembers what I said about combination logic.
Like, it only depends on what happens together.
5 marks. What's your name? Benjamin what? Huh? E? Leave my here. What is the last name? The last name? Huh? Wait. So five. So now, you just have five for 95 percent. Hey, so as I said, combinational logic actually depends on the current inputs you've actually given it. Once you give it an input, the output becomes available just like that, just at once, right? Sequential logic can actually remember. So we have here, I can have combination logic here. Then I said sequential logic combines combination logic and memory, right? So the output depends on not only on the states, on just the current A and B, but on the past ones, right? And then also some of them also depends on the clock. As I said, once you are about to the output depends on the clock. Either the positive edge. We talked about all of them. Either the positive edge, right, or the level. So anytime we are at the positive edge, that is the time we can store data or something. If you are not on that edge, it means that the circuit will have to remember the past inputs they had. Understood? So everything with the coding, everything we've done right now is combination logic. We give it inputs, our outputs become available immediately. So now we have to now find a way to design sequential logic that actually remember, right? They have memory in them, so they remember. Understood? So that's what we are going to look at now. Sequential logic. which you have seen already, which have explained, taking time to explain what a latch is, a D flip flop. What is the difference between a latch and a D flip flop?
The difference
Three
is
five.
combination of latches.
Okay. Go further. I mean, it's true, but go. In terms of storing the data, or in terms of sampling, and then in terms of the clock.
Okay, the flip-flops stores data on the rising and the falling edges. But then the latch stores on the left edges.
What's the name?
Columns, columns, no missing columns. You give me one more right? Let's see, the top, no missing.
Yeah, that's it. So at least he knows the difference between a latch and a flip flop. So he said this.
The flip-flop stores data on the rising and falling edges.
Like this. The rising is when the flip flop stores, or the falling edge. What the latch stores on the. Before we did done this. Understood? So at least one person understands it, then I've done my work. If one person gets. Okay, so now for the sequential logic, we are going to be looking at how to design the flip flops, latches, FSM. I took a lot of time to explain what FSMs are. Then we looked at some examples, right, of the FSMs. Right, so now here we are going to, the most important thing is that once I use an assign statement, assign this to this is what combinational logic automatically, because the input but now I have to now find a way of defining sequential logic. Now we are going to be using statements like what is called the always block, right, to define our sequential logic, right? So now this is what the always block looks like. Instead of using assign, we use this always as some statement here, some variables, and then the statement comes, right? Now, if there's only one one statement, we use begin here and then end it. If there are more statements, we use begin and end. If there's only one statement, there is no begin and end. That now it is your choice, right? Now, if you use more statements here without the beginning and end, you will get an error. So if you have more statements within your always block, always start with a begin and end. The begin and end just means maybe the curly bracket in C. Open and close curly bracket. Right? Are we there? Okay, so this is a D flip flop. So this is just a recap of the D flip flop. It stores on the present. That is the flop. You guys already know what the clock is, and then stuff like that. So it means that at the rising edge, let's say we are sampling on the positive edge. At the rising edge, D will be given to Q. At the falling edge or wherever, the D will be ignored, and then the value within it is what will be seen, right? We know this already. Yeah, just maintain the value. It stores the value. We, we know this already, right? Easy, yeah. So now this is a clear example of the flip flop, and then this is the D flip flop. So here again, but now we have now introduced the clock because the flip flop depends on the clock, right? So now we have this. You just declare your the same way model name. Then you give it your inputs, right? So here our input is the clock. We have the clock as an input. We have input what D or something like that, which is 4 bits, and then our output is the Q, which is also 4 bits, right? So here, if I write something like this, always at the positive edge of the clock, Q is equal to D. So it means that always at the positive edge of the clock, Q will get D. As I said, if you now Q gets D.
What is that the sign outside? The sign
All
left
right,
hand equal to
it just equals to. Understood? So now we have two types of the equal tools, this and this, right? This and this. They are actually different. This means non-blocking statements. The statement is non-blocking, right? Non-blocking. And then this equal to means it is blocking. What that simply means is that, as I said, in hardware, right, your code executes um, in parallel, not like software, right? They execute they execute in parallel, right? But if I have a statement, if I have let's say my always block and I have some statements inside here, right? And I use this one, this equal to, right? This equal to is non-blocking. It will make sure that all the statements are executed at the exact same time, right? Once I use this one, now we treat this like C. This statement will block this statement. This statement will block this statement. So this statement will execute first before this one, then before this one, then before this one. Like C, right? But anytime I use this one, it means that any statement that follows, everything is done at the exact same time. Understood? So we have always at positive edge of the block here is supposed to be easy, right? So means that here they always there's always then some lists come here, right? What that means is that always at anything that happens here, this anything that happens here or anything that changes here, the statement will be executed, begin end, right? So let's say always at A, right? If A changes, is the only time the statement here will be executed. Will be executed. If A does not change, then the statement here will always be there. All the values are maintained. Anytime A changes, like here, always at what? The positive edge of the clock, right? Positive edge of the clock. So anytime there is a positive edge, this statement will be executed. Anytime there is a positive edge, this statement will be executed. Anytime there is a the level or it goes low, this statement is just maintained. All the values here are just kept constant unless we get to the positive edge again, right? So it's very important. This list here, anytime they change, is the only time the statement in the always block get executed. Understood? So this is a simple D flip flop, right? So if we see something like this, Q is equal to D, Q is equal to, you must know that it's just a flip flop, which has a clock. Now, if we see anything in digital, if we see anything like this, that's just a clock. This symbol, right? It means that it has a clock or is controlled by a clock, right? Then you have your D, and then you have your Q, right? Understood? So how will you define or how will you write your code for a large, a D large? Anybody?
Yeah,
Yeah, always at what?
level edge. Something like that also can be used.
Always at what? So now I'm using the same clock. I have positive edge, negative edge, and I have a clock. Positive edge of the clock, negative edge, and then clock. So if I want to describe a large, how will
Always
I
at clock. Always at clock.
another? But
You said what?
Charlie, so now the use always at positive edge. So means that anytime it is only at this point, right? Now, if you want to describe a large, it's always at just clock. Why? Because once you say always at clock, it means that if clock is one, so all of here, clock is one. Understood?
Yes.
But once we say always as positive edge of the clock, it's only at this point. If we say always at the clock, it's at this. So you will see how easy that is. Once I say always at clock, I am trying to describe a large. Always at the positive edge or the negative edge, I'm describing a flip flop. You see how easy that is? If you think small, like the guy here, at least there is one person thinking far. At least. I said at least maybe you two are thinking. Or okay, now a very important thing to is with the combinational logic, right? I didn't put anything or I didn't with the combinational logic I didn't bring in Verilog we have data types also, right? We have YS, we have registers, reg, just reg. Combinational logic, as I said, anytime I always use output probably Y or something. I didn't bring any data type, right? Once I don't bring anything, it means that it's just a wire, right? But for the always block output must always be a reg. If I want to use any statement within the always block, right, like the Q here, it must always be a reg, not a wire. Once I put output, let's say three is zero Q, and just do always a positive Q is equal to there will be an error. It must be output reg. Understood? 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 So they always block the statement inside the or the Q inside here must always be a reg. If I don't describe it like output, if I don't bring anything, it means that it's a wire. Right? Now uh, for the for the hardware design, we always have to reset. I think I said it the last time. We always have a reset state, right? Once you on your system must reset before it starts to execute, or before your code or whatever starts to execute, right? So how do we describe reset in uh, in in our hardware? We have two types of resets. We have asynchronous reset and synchronous reset, right? I mean, you guys know. I think I spoke about what asynchronous machines are and synchronous machine. Anybody? What is the difference between synchronous machines and asynchronous machines?
So you
Oh,
need
master, it's okay. Yeah, it's okay. Anybody else? Because the guy has taken all the marks. But then, huh? What is the difference between asynchronous machines and synchronous machines? I explained different way between FSMs and stuff like that. Somebody is reading that. We have asynchronous machines. I said it the last time, and then we have synchronous machines. What is the difference? It means the words the words there should even tell you the meaning.
So the asynchronous doesn't depend on the clock, but then the synchronous depends on the clock.
Yeah. You saw it on the board, right?
No, 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 sir. Type one.
Yeah, one. This one, yeah, so synchronous machine depend on the clock, while asynchronous does not depend on any clock. Right? Now, so it means that this same thing applies to synchronous reset and asynchronous reset, right? So it means that in the synchronous reset, the reset depends on the clock, or the reset will be effective on the clock. While the asynchronous, the reset does not depend on the clock. Understood? Understood? And so maybe if in case I have something like this, the reset is always like it's always one bit. So we always have something like clock, right? And we always have a reset. Right? We always have a clock in the system, and we always have a reset, right? The reset just means that if you have the board, there are always some push buttons, right? So if a person press, let's say the reset button, then the entire thing will reset, right? So here, and then we have two types again. We have active low reset, and active high reset. So from the name, who can just explain what active low and active high reset are?
So on the active high, there's a reset. Meaning when the reset button is one, it will reset after 0. For the active blue, that's what it means.
Oh, child. Simple. See, simple stuff. Simple concepts. So, oh, yeah. So you see, digital system is actually very easy. It's actually very easy. You just have to understand the concept, right? Active low, active high, it's just ones and zeros, right? The active low means that when the reset is low is when the system gets reset. The active high means that when the reset is high is when the reset takes effect. So you always be told this system is active low reset or active high reset, right? So here, let's say you're using an active high reset, right? So what happens is that if you have, let's say, a D, where this timing diagram is for let's say a D flip flop. We have D and then we have Q. Then we have our clock together with our reset. Right? So if this is D, as I've done what? I should pay you. Oh, okay. Oh, okay, the thing is 5 marks.
Later, active calendar.
We are using Actify Reset. Quite a skill. This is the input to the D flip flop. We are sampling on the positive edge.
After the last time.
Like, I have somewhere. We are sampling on the positive edges. The statement is this is a D flip flop with reset, right? The reset is actified. It means that if it is high, the Q will be zero, or Q is reset. Now, if it is low, it's when the D will be given to Q, right? So, who can draw the output Q? Okay, this one will just be five.
Let me come and draw it.
Yeah, you wait, you wait. Wait. He said, as you explained, like, I said, this is a D flip flop, right? Which is sampling at the positive edges. Positive edge is when I sample, or it's when D gets Q, or it's when Q gets D, right? But within this system, I've added another variable, reset. The reset will actually set everything to zero, or set the output to zero, right? If it is high. If it is low, then the D can get killed on the positive edge of the clock. Understood? Now we are going to reset. We have a reset attached to the D flip flop. If the reset is high, it means that the output is zero. Automatically, it doesn't matter anything else. The output is zero. Now, if the D is low, the D is zero. Right? That is when we can actually sample, or we can store any value.
If the reset is zero.
Yeah, zero. That's when we can store a value.
We can store at the positive.
Yes, that's when, yeah, you can store the positive. So we want to draw the timing diagram for the Q. So now I have D here. This is how D comes in. D is zero, then it goes to one, goes zero, and then we have our reset goes from zero, it goes to one, then it comes to. So it means that from all these points, it's resetting because it's high. Then we can only sample at this point. I've even given you too many hints here.
It's also going right.
Right? Yeah, right there on your sheet. 1 minute.
You have to draw this. The one.
Yes, 1 minute. So once I pass by your place and then you are not
So
and
we
then
just draw the Q or we have to draw the.
You have to draw it.
okay, then I do.
So the 1 minute is T.
This time, how many people will take it on this? It. 50 seconds. Where do I start from?
You have to start with the one.
Okay, so the time is up. Starting from Joshua. Now, it has come down here for some number of block cycles, right? It has come, it has gone, you are close, but it has gone I'll check the way. I'll check the way. I'll check the way. Come so that's why I said it's either one or 100 or zero. Okay, let's continue. So you guys get the idea, right? So here or from here to here, it will be a zero because the reset is high. Zero up to here, right? Then up to here is when it's now checks the next positive edge. Then it will sample D. So D will be high here, right? Up to here. Then it checks the positive edge here. Then it will bring D down. It's that easy, right? But I think because your drawings were the guys who really had it, but your drawings were out of skill. Always, pardon? Nah, they This is just seconds. So from here to here, Q will be 0 up to this point. Very, very important, this point. And then Q will be high from this point because of it comes high, high, up to here. D has come down here, but you see that it's very important. You see that D came down here, but we are at the negative edge.
Yes.
We are sampling only at the positive edge. So this is when D will go.
Is your brain is confused. I didn't know whether the D ended at the positive edge or in the middle or at
The
the
prince is away.
Yeah, okay, but the next time you have to scale. So now, if you draw something like this, right? In case I draw something like this, and then I was my if my Q or if my reset takes effect at the positive edge, right? Then it is what synchronous. Understood? If my reset takes effect, let's say here there is D, right? Then there will be Q. But my reset starts from here. Start from here. Right? So and then this is I'm sampling at the positive edge of the clock. Right? If my reset only takes effect, or if my reset Q on the positive edges, it means that it depends on the clock. Understood?
so this is
That's
asynchronous.
synchronous.
It depends on the clock. The reset depends on the clock. So it means that it's synchronous. It's depending on the clock. Once the clock comes is when the reset takes effect. Right? Right? Now there are systems that are also asynchronous. Once the reset comes, it doesn't depend on the clock at all. The system resets.
Give
Understood?
the example.
Probably let me bring you here. Now here, right? Let's say B, B comes. Let's say we are sampling at the positive edges, right? So here, normally without reset, right? D should start from here, right?
Okay.
Q will start from here, then follows D. Understood? Now let's say we say that our reset is asynchronous. Is asynchronous, right? Now D is here, it starts from here to here. Our reset comes in the middle of this positive edge here, right? If you have a system like this, and once the reset comes, the Q goes to 0 immediately. It goes to 0, right? They mean that we say that it is asynchronous because the Q is the Q will go to 0 immediately. The the reset comes in. It doesn't depend on the clock at all. But this system still means that
Sorry to distract everyone. We are just checking the arrangement for exams. Please ignore us, we are not doing
understood. So here the reset does not depend on the clock. It resets immediately. The reset comes in.
Yes, so give us an example of the synchronous case.
You actually design them yourself.
Thank you.
So
Because when I don't understand the difference, even from the explanation.
so for, as I said, the first step is you can have a D flip flop with no reset at all. That means that the Q depends on only the clock, the positive edge, positive edge. Once the positive edge comes in, it samples. Now you can have a D flip flop with reset. It means that now it depends on two cases: the clock at the same time the reset. right? Now, and I said that we can have a case where we have asynchronous reset. Asynchronous reset means that the system will actually reset without depending on the clock. Immediately reset comes in without the positive edge or whatever, it will actually make Q zero. If I say that reset, I mean that Q goes to zero no matter what comes in, right? So for asynchronous, as long as it is high, the reset is high. Immediately it comes high, the Q goes to zero, right? For synchronous, if reset comes in, it has to still wait to the positive edge before the reset can take effect. Understood?
So, the last part. You said the
I
reset has to
no, no,
wait.
no, yeah. No, no. The reset can come in. It can come in, but the Q has to wait to the positive edge before it goes low. Understood? Again, we can have now. You can have now. We can have first of all, I said we can have a D flip flop with only our D and our Q, right? And then important thing is the clock. Only D and Q clock. Next, we can have one with reset. This is the reset, right? So now the the storing of the value will depend on the D and then the reset. Now we can have another one with enable. So now the Q will now depend on three cases. It will depend on the clock, the reset, and then the enable to store the. They're all very simple concepts, guess, right? What the enable, what the enable does is the enable. Once the enable is high, is when it will store it, right? Once the reset is low, is when it will store. Once the clock is positive, is when it will. It sounds confusing, yeah. But once you go and sit down and then go through it on your own, you understand. So, and I've explained a lot of things. So maybe you just go through quickly. Now, this is an example of the code for asynchronous reset, right? So now here, as I said, if you have the flip flop with only the clock, it only be this, right? Now, if you are going to put, let's say, always a positive and a negative edge of reset, you see that I've added a condition to the always at some condition is here. I said that anytime something like anytime anything here changes is when the safety gets executed. So if I only put positive edge here, right? It means that this the entire statement within here will depend on only the positive edge. If I put in another condition, it means that it depends on this condition or the other condition. Understood?
Yeah.
Is it
Is it
all
all or
Or,
none?
or, or, or.
Wow.
Understood?
Yes.
Don't get confused.
yeah,
Yeah, or, no, not and. Minus one. That's you are
What
just.
the kind of advance?
Understood? So it's all positive edge of the block or the negative edge. So anytime any of them changes is when they will change. So this is what an example of asynchronous because it doesn't depend on the clock, it depends on the reset also. Once the reset changes, immediately the code will get immediately. Right? Understood?
Yes, sir.
Very easy, right? So here it just means that if reset is low, then I come and check the conditions here. Just
what you said that like example whether it is active or active, does it talk about it?
yeah, yeah, yeah. So here, if reset is equal to zero, it means what? active loop. That what? What have you done?
Say once more.
Okay, you the next person will thrown at you, so for free 5 marks. Okay, now let's continue. So as I said, if you have more statements within the always block, you use begin and end. Okay, now so for example, a system like this, you see that the condition is just always at positive edge. It means that everything gets the entire statement here will be looking at the block to get executed. So here is what?
I mean, the diagram is just with clock.
Right, so this is synchronous. The reset depends on the clock. Easy, right?
Yes.
Now, as I said, there can be an enable also. So you just go through them and then.
So the ones with the enable and the clock is not synchronous.
No. We are talking about only the reset. Yeah.
So what I mean is that at the point where it depends on the clock enable, it is
What
synchronous.
depends on the reset
The
or
reset
yeah,
depends on the clock enable,
yeah.
is synchronous. But when you add enable to it, it becomes
Now the enable is not has not has the enable doesn't have anything to do with the reset.
the reset.
Uh, Understood? Shall I continue?
So agree.
Yeah, let me see where. Let me just do one thing. Let me just because let me some few slides. Let me just okay. Let me just okay. This is the large. You understand why it's a large?
Yes.
Why is this a large? This is the code for a large. I've already explained how the large works. The flip flop. We have explained flip flops, right?
So 5 marks.
Now, now this second use mark. So
Sorry for you.
I've explained the code for. I've explained the code for flip flop and why it's a flip flop, right? Now on the board. You got 3 marks, right? So now this is a large. Why is it a large? Okay. Now, if you waste my time, it's minus 5 because you didn't do and I just told you 3 marks. Once you waste time now, minus 5.
Because there's a condition
Yes.
after the always at work. Say if work is less than
It's equal to
it's always at work if only u is less than or equal to.
let that people. Yeah. I waste my time now. Master minus one, this one is here minus I like this. But this is very serious. Less than or equal to Master.
The explanation. What
Hey, master. You have just disgraced me disgrace. Hey, this guy disgraced me So if you go anywhere and then somebody writes something like this, then you say it's less than or equal.
explanation is what I understand.
Master. You have defamed me. Oh my God. The film left me, master. So,
I'm sure that like this one is it's only club. There's no positive. I'm not explaining.
okay.
Let me say
You said the deep flip flop is always at the bottom top. But this one is just at the top.
You mean like on the level? right? And so if you say always at clock, it means that we are using this is a clock. If you say always at president, it's at this point. If you say always at the clock, it's at this point. Understood? So minus 5. Okay, so within your code, you can have so many always blocks, like so many always blocks within your code, right? Now, but the same the thing is that, as I said, the always blocks must always be a red, like here. This is special, so red. And then this is what? Again, okay, again, 3 months again. This is well, that's already something like a sign. What is it? Is it combination logic or sequential logic?
This one is conventional
Is it combination logic or sequential logic? Why?
they are assigned. It's just a while. There's no red.
Okay, half. So why? Anybody else? Why is this combination logic there? Just here. Just a
Because of the weather.
No, not just that. So you mean that just because of the way that sign is combination? This guy actually explained it the last time. What combination logic? But of course, combination logic always start with the assign. That one. Right? So like for a code like this, in your normal codes, you can have combination logic in there, sequential logic in there. So you always look like something like this. Now the condition is that you cannot have the same assignment to the same to two or more always blocks. So if I have special here, right, in one always block, it cannot come in another always block. There will be an error. It must always be in only one always block. Right? A variable assignment must occur in only one always block. Understood? So let's take some break, then come and finish up. I say half. Okay. Let's come at 12. The slice. It depends on the slice. It doesn't depend on.
Put your half, the minus your half.
This one.
Yes.
I'll give you one. You see how you see how I get it? I did it there. Yeah, so 11 is so many. And we have to finish it today. Oh, but the rest are just basic stuff. So I'll just glance over there. Huh? If you complain, -1 or something like that. Because this is supposed to be 6 hours in a week. But so far, from the time you started, we only do about 1 hour, 2 hours. Then just 1 hour, 2 hours there. So maybe let's take some 10 minutes break, then refresh, then come back fast, then just finish up. Then use some 10 minutes to finish. Use some 20 minutes to finish up. So let's come at 12:40, 10 minutes. Just 10 minutes to refresh your mind because 10 minutes break, 10 minutes break. It starts now. Now, if you don't come back, 10 minutes, 10 minutes. So talk what? Like, come on. Now you come back. I was yeah, I mean, to what? You said it, but so now, that's for high school. That's for high school. I think there's some career center or something. They model controller and it gets counter. And you don't want to say, I get busy. I don't know where
class for the dates, the class you're running for the class during the exam, it's very
that one is intensive because and the class is but the class attendance goes back there. That one is needed because
When you are saying either 0 or 100,
oh yeah, that one is that one. So it means that at least if you do your homework, you do your labs. By now you will get about let's say 50% of them, and then the exam will be like what 50%.
so the assignment, I couldn't do one.
Then your plus mark there.
So I should be fighting for the 5 marks in the class.
When? I don't know. No. Nobody has told me about enemies.
Just give us normal assignments, then you use it as what is it?
You can say I get time or something. You guys need let me see. It's on your desktop, right? What? After that, about 5 minutes today. The same error. The same error.
Then what they are using
They
is
have one overhead, overhead, always overhead one.
Maybe it was your design. Maybe you have made an error. Go through it again. Go through the code again. Okay, okay. Let me finish here. Ah, really? Please, let's continue. I want to leave here. We close. When the slice is finished. So we have looked at the always block for designing our flip flop and latches, right? We have looked at the always block for designing the latch flip flop. We have seen all of that, and then we have seen that the latch and flip flop can remember, right? But the always block is not always that it remembers something, right? For instance, if you see a code like this, so once you look at the code like the always at INV data, if INV is equal, if INV results is equal to not data, else result is equal to data, right? Does this code remember? Or is this combination logic or sequential logic? If I say combination logic or sequential logic, it means that does the code remember? Or does it store anybody? Does it store anybody? Does this code store anybody?
and go by the what is
And then it gets a variable. So you can draw, when I look at this circuit, I can draw the circuit for the circuit. I can draw the circuit for the code once I go through the code, right? Or no? You guys can do that. So does this code remember anything, or does this code implement a flip flop, a latch, or combination logic? So from the word group, once you see always as inverse or whatever the values are, there's no positive edge or negative edge. So the is not a flip flop. But it can still be a latch. It can still be a latch. But is this a latch or not? Does this code store anything? Why? Huh? Because what? I said the always block is used for making the latches and flip flop that can remember, but it's not always that it can remember something, right? And then this is just a clear example of where the always block is not remembering anything. This is so I said, can you know the secret for this one? Anytime you see an if else statement, right? and I've said before, anytime you see an if else statement, it will implement what? A multiplexer, right? Or no?
Yeah, you said.
So is this a multiplexer or not?
It
Please
is
hurry up and let me
yeah,
read
it
here.
is a multiplier.
Why?
Because if if is INV is true, then we we get not data. But then if it's not, then we get data.
So once you something like this, you can easily just draw it, right? If
So if it's
so,
one,
it means that our selector is in
yeah,
INV, right? We have what? Data
data,
as our input. We have our output to what? Results. And then this is if it is one. If it is one,
there is a zero base.
so we have 0 and 1 here. So if inverse is 0, right? It takes data. If it is 1, have you guys seen it? Anybody? You see how uh,
We've seen it.
have you guys seen how it works?
Yes.
So the data circuit is simply combination logic that implements something like this. So it doesn't remember anything. There's no flip flop inside here. There's no latch inside here. It's not trying to remember anything. Understood?
Yes, sir.
If I remove the else statement, what happens?
If you remove that
Now,
line of code,
now the same thing. The same. Just try to draw it. If I remove the else statement, what happens? Does it remember or not? I'm trying to draw up your attention to something. I want you guys to just think for yourself and see something. Right? Now, if I write if INV or index or whatever, the result is equal to not data. Else, this code I don't remember because if you implement something like that, there's no feedback loop or anything that will make it remember anything. Right? Now, if I remove the else, if it is only if INV results is equal to not data or power.
just remember,
Why?
because when if is high, the not data always
And if it's low,
it is still there until
5 marks. This is just simple thinking. Oh.
you
You
know
see,
You're not writing down.
yeah, this guy doesn't have to write any answer. Very, very simple, right? Now, we are saying the IMB is just one bit, right? It's just one bit. And then we are using an if else statement here. If it is this, we assign some value to it. Else, we assign the value to it. This is a full case of if else for a one bit. If not this, so it means that every time there's a value assigned to it, right? It is taking the current inputs every time. It doesn't remember anything. Now, if I remove the else, and then if IMB, it will take a value. But what if it is not IMB? If IMB is low, what happens? It has remembered. It takes the past value. So the circuit will remember if there's no else statement here. So it means that you have actually designed a latch and not conditional logic. In effect, in case you are trying to design in case you're trying to design your hardware, you must be very, very careful about what you're doing, and then you must know exactly what you're doing. If you intend to design combination logic, and then you're using if-else statement, it must be the full case of the if-else statement, the full case, so that anytime, so that in every state it will assign a value, right? Once you remove one state or one state from inside, you are describing a latch. You have this, that is no longer combination logic. It's a latch. And then it is going to cost you more hardware, more area, more power consumption, and stuff like that. Right? Even though it might work, because here, it might work, the circuit might work, but it is costing you more. Understood? Understood?
Yes.
So this case is combinational logic, not sequential logic. There's no memory inside here. It doesn't remember. Right? So this is very technical. Just a little bit. But if you think about it, you will just understand. So for 5 marks, the two, or we are looking at out A and out B, right? For the two codes, will out A and out B be sequential or combinational? Will it remember or not?
So to remember.
Which one? I mean, let's take the first code here. Okay, now in the first place, anywhere you see always at star, it means that it means that every variable within the code is within here. Understood? So you saw that sometimes I use always at, let's say, only the clock or something. So it means that we're using only the clock. But if I'm using always at start, it means that all the variables are within here. So if any of the variable changes, the code will get executed. If none of the variables change, then the code is maintained. Understood? So if you say always at start, it means that all the variables. It means that here, how many variables do we have? We have enable, we have data, we have out A, we have out B. So the always at start means that always at enable or data or out A or out B. All the variables are inside there. Understood? So if any of them changes, then it means that the circuit will change. Now here, if I say always at this, always at theta, right? It means that anytime theta changes is when the circuit gets executed. But anytime anything else changes, the circuit doesn't get executed. Understood? So they're simple concepts, right? So now if I take the first code, always at star, then the code comes in. Is out A combination logic or sequential logic? Is out B combination logic or sequential logic? Does out A remember or not? Does out B remember or not? Hmm? So out A. So now we are talking about A. So you said out A, it doesn't remember anything. What about out B? So let's start out A. Does it remember or not? So it means that it's combination logic. And out B. Now in the bedroom, why are you saying out A is combination logic?
Staff over there because when any of them changes, it affects.
It affects what? Out A or out B? Then how about out B? But you see the out A is within another statement here.
So I think that the staff of them still affects.
Yeah, of course. Okay. Out A. Let's analyze out A, right? So let's see whether out A remembers or not. Right? In the first place, if anything, always at start. If anything changes, right? What happens? Out A first of all starts from out A is equal to 0, right? Before it comes into the if enable. Then if enable has changed, then if enable is 1, then data will be given to out A. That's what happens, right? So anytime anything changes, the out A will go to 0. Then it comes to check if enable, right? So it means that out A remember or not. It doesn't remember. Because every time anything changes, it goes to 0. Right? Now look at out B. Does out B remember or not?
Remember,
Why?
because the when anything changes, it doesn't affect us.
Now when anything changes, it will come and check. You see that when anything at all changes, right? It will come and check. If enable is high, it's when it will assign the value. But what if there's no enable? What if enable is low? it will remember.
To maintain the
To
value.
maintain the value, it will remember, right? So in this circuit, our A is computational logic, our B is sequential logic.
But
If
then both of them have combination logic.
Master, we are dealing with only one thing here. We are dealing with only one. So now we understand from this perspective, from this side, right? Pardon? Please, do you understand? Because some of you understand. I think this guy understands. This guy, Master, do you understand? Do you understand? I think this guy understands. This other guy understands. So do we continue? At least two people understand. Yes, explain to them.
The reason why is combinational and sequential. Like, if based on our steps, meaning if anything in the system changes, then out A will be assigned with zero. The one comma approximately B zero means zero will be assigned to one bit zero will be assigned to the out A. Then after that, it becomes a check if enamel is high or not. If enamel is high, then assign data to out A and assign the same data to out B. So in that case, if the changes if the service anything changes in input, out A will be set to zero. But then out B doesn't go back to zero, meaning the data in out B will be stored. See, when you have the out A equals to one approximately B zero, you don't have the B there. So meaning the B will never be set to zero. But then it just maintain its value when enable is low.
Are we getting it? Huh? No. Okay, why? They're looking at A or B whether they can remember or it only depends on the current inputs, right? That's what we're looking at. And then I said for the start, it means that all the conditions are there. Enable, data, out A, out B. Right? I'm just going over once. Right? So now always ask if anything within the what do you call it? If anything there changes, right, it's when the code gets executed. If nothing changes, the code is just maintained. Like all the values are just stored like that. Nothing changes, right? So if anything in the always has changes, it will come into the code. Now, anytime anything changes, what happens? The first thing it does is that out A will be assigned 0. So it means that there's always an assignment to out A, no matter what. Anytime anything changes, out A gets a value. Anytime out A changes, out A will get the value. Now, then if you get into the next code, if enable, now you can see that out B is only assigned if enable, right? If enable is high, right? Even both of them are actually assigned if enable is high. But the point is that the out A, because it says it will be executed first before we get into the next section of the code, right? So now if enable, right, out A will be assigned, out B will be assigned. But what if there's no, what if enable is 0, right? So here if enable is 0, out B will maintain its value, and then out A will get a 0 because out A has already been assigned already. It was assigned before it even got to the even level.
Doesn't mean that the out A in the given statement is not really affected by the new statement.
It is. That is when if is 1. But first of all, what it does is that it will enter, once anything changes, it will enter, then it will assign out A to 0. Then it will go to if. If enable is high, then it will assign a new data to the out A. But if enable is low, it means that it will get the value 0. So now, let's go to the second one. If you guys understand the first one, then the second one is just the same. Right? Now here we are using it is not all it is we are not looking at all the conditions, right? we are looking at only always at data. So if data changes, it's when the code or when the code within the always block will be executed, right? So here, let's look at it. If data has changed, what happened? Out A will first will be assigned 0, out B will be assigned 0. Then we go to the always block. And then if enable is high, it's when out A will be assigned, and then out B will also be assigned the value. Right? Now, what if enable is low?
Keep the previous zeros.
You keep the previous values. Right? And then again, within the same code, what if data does not change and the enable changes? If data has not changed but enable has changed, what happens to the code?
Anyway, it still hold the same.
It will hold the previous value, not the zero. It will hold the previous value because enable is not in the list of. Understood?
Yes, sir.
So this both, so means that here both they are both sequential. Understood? Do we understand? All right. So and the next thing is that they said the always block. You don't they always block. You write more code with the always block. If you're doing combination logic, you write more code. But if you are just using the assign, right, your codes are actually shorter. Right? This one it just depends on you. It's your choice. So you can actually use the always block or the assign statement to design your combination logic. Understood? Now, now if you have a code like this, right? This is some of you are using Arduino for your web, right? For your projects, and then maybe you might have 7 segment display there, right? Who is using Arduino with 7 segment display? Huh? 7 segment display with Arduino. Who? Huh? Who? Ah, really? Why? So now it means that nobody is using Arduino. Huh? Not with what? So this code is just 7 segment display, and this is display point. Now we have if else statement, right? Instead of the if else statement, you can use case, just like in C program, right? Yeah, I think it's right. So now here, like in case you're writing your if, you write if, then some condition, some then else, right? Here we use case. You write case, and then the condition comes. And then very important, you use end case to end the case. Case then end case, your condition comes, and then your statement comes. Right? Now here, for the 7 segment display, probably you guys have seen before, right? Yeah, you enable some LEDs, right, within the display to actually enable a number or whatever, like this. Probably this A, B, C, D, E, F, G, right? So maybe if I want an 8, I have to on A, B, C, D, E, F, G, right? You guys know this already. If I want maybe 0, I have to off this one and on all the rest. Right? So this code is just 7 segment display. Hey! Lights out.
Now we have the data.
Okay. Let's let's just freestyle it and go away, right? So please keep quiet. This is the service segment display, and I can't write all the code down here. So it means that for the point with the service segment display is that now you always start with like case data, right, and then probably end case here, and then you start with the value. Data here is 4 bit, so it means that we can actually take numbers from 0 to what 15, right? 4 bits, 0 to 15. So I can start 4 bit decimal 0, right? And then give it, I think it was the output is segment. Segment is equals to some 7 segment display. The value the A, B, C, D, E, F, G. So 7 bit binary, some value, right? Then we come again, 4 bit decimal, let's say 1. So it means that here I want to display a 0. So 4 bit decimal 0, then the segment will come. Then it will, let's say, if we are starting from A, B, C, D, E, F, if it is E, F, G, E, where is F?
You repeated the E.
A, B, C, D,
You have two
E.
points. No, the first one, the top one.
So A, B, C, D, E, F, G, right? What is here? If it's 1, it means that it is on. If it's 0, it's off. So if I want to display 0, right? So how will it be? Let's say we are starting from A. A is what? 1, 2, 3, 4, 5, 6. It's 6. Probably like 1 somewhere. This is 1, 1, 1, 1, 1, 1. Then the last one is 0. Understood? You see how easy that is? I've displayed the 1. If I want to display a 1, what is it? A 1. Whatever. Now here, because there are 15 of them, and then let's say I display from 0 up to 9, right? What happens to the rest? 10, 11, 12, 13, maybe, and I want to assign them to a 0, right? Just assign 0 if it's 10, 11, 12, 10, 11, 12, 13, 14, 15, right? Now, if I don't do that and I just design up to here, up to 9, 0 to 9, and I don't do anything, it means that because this is an incomplete case statement, right? Incomplete case statement, and then it will be a what? A large. But here we are going to design combination logic for our service segment display. If I do from 0 to 9 without bringing anything, it will be a large. It will still work, right? It will still work, but it will be a large. And then a large will use more gates, right? So what I can do is that if I do up to 0 to 9, I bring something called the default, right? Segment is equals to 7 bit decimal 0. So that anytime it is not 0, 1, 2, up to 9, it will just give 0 to it. Now here I've defined combinational logic, right? Not a large anymore. Understood? That's how easy it is, right? So, yeah, that's how easy it is. So now in the labs, right, you might design your ALU, your memory ALU, and then you'll combine all of them, right? And then you want to test the IAC, the instruction set architecture, right? So it means that, and then they're using machine codes, right? We give machine code to our memory, right? And then the memory will read the machine code and assign it to the ALU or something like that. So if you want to display the results, you're going to display it on the 7 segment display. For instance, if you're adding, if let's say your code is saying add add two numbers, A and B. So it will add the two numbers and then you display it on the 7 display to see whether it works or not. Right? But that is the end goal of this entire course. Understood? Yeah? But then, so that's the end goal. But you are designing your AL, your memory, all those things with Verilog. After that, you have peripheral, the 7 display, you have push buttons, you have the dip switches, and then you want to see if what you have designed it works, right? So we have to give it some inputs. You have to give it the machine code. Maybe you are using the dip switches, you give it the machine code. If it's one, if you push the dip switch up, it's one. If you push it down, it's zero. So we use that one to input our machine code. The machine code will get stored in the memory, right? Then it will read from the memory to the ALU. The ALU will provide the results, give it to another memory. Then we read from that memory to our 7 display. Easy. And then that will be your end of semester project. Finished.
End of semester project. We have another project.
For this course, not your Understood? So now, as I said, we have non-blocking assignment. This is also important. So I have something like always at a so this is non-blocking assignment. That's what I said already. It's non-blocking assignment, right? So now if I have a here, if I have, let's say the values are, and I start with the value 0, 0, 0. So it means that A starts with the value 0, this is 0, this is 0, this is 0, everything is 0 here, and then C is 0, right? Right?
Yes.
If I start with all zeros. Now, if I change, let's say A to B to, no, I change B to 2, I change D to 2, right? I change A to 2, I change D to 2. So, what happens? What is A? What is A? What is C? Why? This is very, very important. Now, this is very, very important. A very, very important concept in hardware design. Right? I said, first of all, we start with 0, 0, 0. Once everything is 0, we know that everything here, A will be 0, B will be 0, right? Oh, then today the 3 hours, or even 10 hours, 11 is 10 hours. Yeah, it's time. We are doing 6 hours course. If you want to live there, this is the university. If when you can go, there's no anything there. Please, so analyze this. So first of all, I start with 0, 0, 0. A is 0, B, C is 0. So now, what if I change the B and D. So what happens? What is A?
So you get
So now I'm coming for your explanation. Explain for 5 months.
is non-blocking assignment. So all the codes execute at the same time.
I'm coming. I'm coming. My battery is low. Right? It means that somebody here is just is just speaking against me. But hey, what's that? Who is it? Who is it? Nah, the battery of. Somebody's working against me, pal.
So it's not from here. It's my
Yeah, it's not from here too.
what's from here. I don't think the lights are. Okay, I think it's
What is so now? What is A and what is B? Sounds better. 5 months old. Who to what?
so because they don't run parallel, they just all run at once. So
They don't run parallel.
like they don't run line by line. So the second one is not dependent on the first one. They all just run.
So 5 months. So 5 months. Explain the
Hey, drop it, stay. And it's fine.
So 5 months. 5 months.
Wait. As I said, the dictator, everybody has their own thing, right? This one is right. Let me hear it.
Non-blocking assignment.
This way.
So all the things are run at the same time.
Yeah. So mean that it is using the previous value of A.
Okay, yes.
Understood?
Yes, sir.
That's what.
So last difference.
I have
5 months. So mine is now 8. Calculation.
okay. Huh? Okay. 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 Free mark. Let's go. First of all, now you. So A starts from 0. So we are starting with 0. Next we change B to 2. D to 2. What is A? A is 2. C is what? Why? Hmm? It will take the previous value. Defend your answer. Okay. And I gave you the chance to get 3 marks. So who else? What is A? I gave you a chance to get 3 marks. Go. Why?
Because this is using the blocking assignment. So when the first one is running, the next one will block it from running the second one.
So mean that this updated value of 2 will be here. 2 plus 2, which is 4.
Yes. 5 months.
Another number. But you have had enough marks, right? Alright, so but you didn't explain. Your explanation was off. Yeah, the explanation was off. So just go through it. Let's move fast. So you can go through it. I've given an example there that you can easily understand. So just the rules are that always use non-blocking with the positive edge, like to depict your fifth lobe, right? And always use the assign statement for combination logic, right? And then another rule is that I think I was saying that once you have two or more always blocks, if you have two or more, you have two or more blocks, right? Always block. You can't have A equals to B. The A must be in only one always block, not in two always blocks. It will give you an error. It will give you an error if you do that. So the last thing,
Let's leave this one for later. I think that is complicated.
oh no, the one is even far easier. So this is now we have now we know how to design combinational logic with Verilog, right? Using the assign statements, right? We know how to design sequential logic using always a positive edge, right? Now we're going to do the FSM. You know that the FSM combines combination logic and sequential logic, right? So this is the FSM diagram. You already know this. I've taught this thing over and over again. I was chat here. Eh? FS, FSM. What is it? Ha! Sequential logic. I've already explained it. So there's just a recap, just some brief recap, then you just do the good way, then I go away. But it means that what we are saying, what is that? What is that FSM part? It doesn't skip me. You have no going to it. Finite. Then 3 months. F is finite. The next is what? Okay, yeah. FSMs are get funny machines if you have not gone through the so this is how it looks like. Eh? No. What's that? So the FSM looks like this. You have even designed it though. I even gave you some assignment to design the FSM and everything. Right? So the FSM looks like the circuit for the FSM looks like this. The FSMs are very, very important in digital systems. You design you design your hardware with it. So quickly, so the FSM has inputs. You guys don't know this already. It has inputs. Then the input goes through the next stage logic. I've explained this already, right? Then we have the stage register. Then the output logic, right? So here, because we already know what this is, we are going to use all our knowledge in Verilog to design this FSM, or this to design an FSM. So the FSM has the state register, which is made up of sequential logic. I've explained that. And it also has output logic, which is made up of combination logic, and then the next state logic is made up of combination logic, right?
Yes.
So you will be given a statement like this, right? The output, Y is high for one clock cycle out of every thread, right? The output, just look at the clock and look at the output. Why? You see that the output is high for one clock cycle out of every 3 clock cycles, right? You can see it, just must look on the board. Just look on the board. So I'll just give you the statement, and then you first of all draw the clock and then your Y. So if you don't understand how the statement works, so that's why I said it's either 0 or 100, right? If from the onset you get the statement wrong, or you don't understand the statement, and you draw this thing wrong, everything you do is chaff. Nobody is wrong, right? So you must understand the statement to be able to draw your timing diagram, to be able to draw the state diagram, to be able to write your code. Understood? So here, I'll just give you a statement like you have a clock and then you have an output Y. The output Y is high for one clock cycle out of every 3 clock cycles. So draw your timing diagram, draw your state diagram, then write your Verilog code to execute your state diagram. Simple statement. Then like 20 marks. Understood? So what about equipment like so means that here the clock is high for one cycle. Out of every 3. So you will count 1, 2, 3. It goes high for one cycle. 1, 2, 3. It goes high for one cycle. Are we getting it?
So, but for one side, you have to go
Yes, that was the.
one, two,
It's high for one cycle, then every single cycle.
it's good for 3 cycles. Then come back.
Yeah. So it counts. So when it has gone low, right? It counts from that point, that positive edge. I'm missing it. This edge, right? I'm missing it. So from that point, now from that point it counts 1, 2, 3, go high. Then go high for one cycle. Then count again. 1, 2, 3, go high. So this one, it just repeats until infinity. Right? It goes yeah. Huh? Can you? It is already here.
So the thing is that for a full cycle for the clock, you have to
You
go.
have seen it, you have seen it. Look at it, what I get ready.
So let me think of that. Let me see that some.
It starts, let's say it has come down, right? It has come down. And then you just here,
So use the stick.
So that's what I'm saying. Then that's
they are starting here. Yes, they are starting here. Yeah. And then they just give up on 2 minutes. You guys press me your head. So we are here. This is how I am doing it. You can actually understand it in your own way. But I'm saying that it should be high for one clock cycle. This is one clock cycle. One clock cycle means that from one positive edge to another positive edge is one cycle. Okay. Right? So now here, let's start from here. It counts 1, 2, 3. Then it goes high for one clock cycle. It goes high. Then it counts 1, 2, 3. Then understood? Yes, sir.
So now, so the other business I'm going. So when we're doing the when we started this, we told us that the one cycle means from one positive edge to another. That's one. But then they said three block cycles. If you count.
And we are starting from when it has gone down. This is the one clock cycle. One positive edge to another.
Yes,
So
that's one.
fine.
Then another one, 2. There's a block 3 for block
I said
cycles.
this is one clock cycle.
Then that's 1.
And then another clock cycle starts from here again, not
The next one.
from here to here is another clock cycle. So if so you can talk about it like I'm starting from 0. I'm starting my system from 0. And then I'm starting from the positive end of the clock. So if it is 0 here, right, my first count will be from this point. As it is, your first count is from when the Y has gone low. Right? So we start from there and count 1, 2, 3, then it goes side, 1 goes side, and then from where it has gone low again, 1, 2, 3. Okay, so let's continue. So now with that, I can draw from this statement. You will draw your state diagram, and then your state diagram. Everybody will be actually different. based on how you think, based on how you do your timing diagram, right? So here, this is one way. It doesn't mean it's just the only way. Here we have our we start from stage zero, right? Here we are starting from high. Let's say it is one. Y is one, right? From stage zero, we go to that high one cycle. We are going to stage S1, and then Y goes slow, right? Then it goes to stage S2, then Y goes slow. Then it circles back to stage S0, then Y goes high. For one cycle, then you see how it works.
So, how would you draw this to depict
You actually draw it to depict it.
So how do you get a missing?
You will draw it you based on how you are thinking. That's how you will draw it.
So like how
So
do you
here,
how do you for this one?
so here they are starting from a high, right? They are saying, let's say, they are starting from here. Y is high. Y is high. So if Y is high, what happens? Our next state is go to state. Our next state goes to the next positive edge, like this. We are starting Y from here, the first positive edge, right? And then Y is high, and Y is high for one cycle. So the next positive edge, Y goes low. So it means that we have moved to state S1. Then Y is 0, right? Then we move to another state, state 2. Y is still 0. Then we move to another stage. So we have started 1, 2, 3. Then Y goes high. You see how simple that is. But that's how they thought about it. What?
Is it this one is from this drawing you can't tell whether the difference between a state and a state is 3 cycles.
Yeah.
You can't tell.
You can't tell. But
But from here you can tell.
You don't think of it.
and I use the state to draw something like this. Understood? Understood?
Yes, sir.
So what I'm saying is you see the white goes up one side. Then it goes to
Yeah, so that's how I said I drew the checkbook like this. And I said in case you're using this state, you will get the timing diagram right. You start here, they are starting from 1. They are saying Y is 1. So means that at the positive edge here, Y is 1. Right? Y has gone high here. Then Y must come low when? The next positive edge. So from here to here is one cycle. So Y must come down. So here is here is another positive edge. So Y comes down here. Right? But we have moved to another state. State S1. Then Y has come low. Then we count again. The next state, Y must still be low. That is another count. Then we count again. So we have moved to another state. S2, Y is low. Then we count again. The next state is that Y must go high. So Y comes high here. And then we continue. So we have counted 1, 2, 3. 3 cycles. It comes high. It stays high for one cycle. 1, 2, 3. 0 cycles. Any confusion? So easy. Okay, you can go home and wait and sit down there actually try to analyze. But yes, the point here is that so now, I need some time. And I've talked here for like hours.
Even if you keep going on, you start getting
We are done. We are done. 11 like 2 slides and we are done. That's why. It will produce. This is just easy. So first of all, how my state, and then for the state diagrams, and I've already explained it in the last lecture. So the next stage is we are going to now write up. So here is very important. We are going to write the codes to execute this state diagram. Masa. So we are writing the code to execute. We are writing the code to execute this state diagram, right? Then, as I said, from the last lecture, from the FSM lecture, we said that we have to encode the states. I talked about encoding the states, right? And then I said we can use some two forms. So here, I start off with my input clock, reset, and output kill, right? It depends on you. However way works for you. Then I encode my state. I say my state S1, S0. I have three states. First of all, I have three states: S0, S1, S2. So I can use 2 bits to encode my state. So I say state S0 is 00, S1 is 01, and S2 is 10. We did this already. The thing is body. So now I come and declare my states. Parameter S0 is equal to 00. Like, and then it is just 2 bits, right? It's 2 bits, right? So I declare here, register here, 2 bits to hold my state. Understood? So 00, S0 is 00, S1 is 01, S2 is 10. Parameter. The parameter means you are just declaring something like a constant in C. You've declared a constant. You have assigned a value. You assign a constant to a variable, like in C, right? Or how do you assign something like constant? Is it constant or something? Constant. Something like that. So it's parameter A. So means that anywhere you see A00 is just to help you understand the code better. But it is actually 00. It is where you see A0. The code knows that it is 00. Just like const in C. Right? I do that. There are 3 of them. 000. Now, my next is how to update the states. Right? And then we said that what? The state gets updated at the positive end of the clock. Right? So at the positive end of the clock, the next state will be given to the state. Right? Look on the board, right? So I have always at positive edge of the clock, positive edge of reset. What type of reset is this? For 5 months. Synchronous reset.
Yes.
Look at it. It's what? Why? Why? Always at positive edge of the clock or positive edge of the reset. Why is it synchronous?
So because it depends on the clock.
Anybody else? Master, you guys can this up from far. It doesn't depend on the clock. Because it's only a complete clock or another condition. Another. Yeah, that's what it is. Understood? So, and then, is this active low or active high reset? 5 marks, active low or active high? Active low. Why? No question, there's no question. I'm talking about the code over there. Now you wait. I think somebody said active high. Why? Massa. Always look at. Always take small. Yes, small. Take. Is it active low or active high? And I've seen you consulting over there. Okay, why? Then, if you don't get it right, then 0. Hey. Yeah, no. Please, how do you go? What is 1? Because the clock is 1, right? Yeah.
The reset goes high.
Nah, it's just.
Then because you have if reset,
Mhm.
the reset is already high one.
You mean like
If reset,
if it is one.
yeah, if reset, if reset is one.
So if it was if it was active low, what would have been here?
Reset because it was zero.
Huh?
If reset it was zero.
Or just something like if not reset.
The days back here,
Then
bonus.
my mouth, then you are not even my mouth.
Bonus. Oh, so.
I can't even take my mouth.
Your master, your way is good. Your explanation is not good, Your explanation is no good. Explanation is no good, And so now, so here we are updating the states, right? So we say that if equation x is a block, the next state here is using the states. Simple, right? Right?
Yes.
So now our next thing is our the next one is the next state logic. Yeah.
That's like
That is from time. So we are doing the next stage logic, right? And then the next stage logic will define how we move or when to move from one state to another. Very, very easy. Right? You use case always at home, then case state. So if you're in state A0, what happens? State A0. Next state is what? S1. Right? You just use this one to draw it. State A0, the next state is S1. Easy, right? If you're in state S1, the next state is S2. Why? The next one, our next state goes to S2. If I state S2, our next state is S0. Now, this represents it, right? But you know that our state is two bits. So if you have 0, 1, 2, 3, 4, right? So if I usually say S0 is 0, 0, 0, 1, 1, 0, part of 1, 1, what happens? I just use the default here. Next state is not 0. If I don't do this, what happens?
You have a lot. You have a lot.
You have a large,
Right, Max.
not combination logic. So yeah, Hey, you just answer. What the question can just answer, right? Your answers are always better. Oh nah, how? This is our next state logic. You see how easy it is. Just using the state diagram to design it, right? The next one is our output logic. Output logic. Right now, the Y is our output. Y is our output. So what logic can we design to depict our Y? Right? So if state, so once look here, if state is equal to 0, our Y is 1. Right? So I use the comparator here, state is equal to 0, then assign it to our state. It's as easy as that, yeah. This is an assigned statement. So our output logic must be combinational. The only thing that is, like I said, we have output logic, mistake logic, and the statement, the stage register is the only thing that is sequential. The rest are combinational. Understood? So now, this is very important. Now, as I said again, everybody must have a different answer, right? So we have something like this. State is equal to state is, we compare state to 0 and give the result to 0. Can anybody design it in any other way? Any other way? For 5 marks? Very, very easy, right? State is equivalent, if state is equivalent to A0, then just assign the value. So here, if state is, if here is 0, then here is 0. Here, 1. So, can anybody do anything about this one? This is just one star. Huh?
I know about it.
Okay. Okay, you were always complaining that some people are getting the marks. So, okay. 5 marks, quick. So, can I design this? Here, can I design this using any other method? In your view, just take small in your view. Or all what you have done. Can I design it using logic gate, sequential logic, whatever? Yeah, right. And let me see. So you see, he is the only one going to write it. You're also saying that, but you want the marks. 3 marks, 5 marks. Any other way to represent the scale is equal to state is equal to this. Right. So if you guys can write it, then the next one say the 0 and then 0 but no, yeah, the 2 was you're getting 0 now just design just small. This is a very small circuit too. Just anything. Are we done?
So it's 2 bits, right?
Huh?
2 bits.
Yes, the state is 2 bits. State is 2 bits, yeah. So state, I think the 1 is to 0. You can do this in like 20 different ways. 20 about 20 different ways. So that was it. In negative system, based on how you are thinking, completely different. Your results will be completely different. And then your hardware gears will be completely different. Your everything will be different. But it will be the same execution. It will do the same way. Uh-huh. If S is that one is
10 months, 10 months. Who is wrong? Firstly, he said 10 months. Oh, say 1 month, you're right.
What someone has done is like this. You supposed to if S what? If state equivalent to 0, 1 or else 0. So this is another way of doing it. That will result in the same answer. So anybody else? A different way. So, what's your name? Your name.
Then ask the German.
Say, let me the switch case. Where's the switch case for you?
So you see, there are more ways.
Yeah, there are.
But me, what I know goes on the mind.
Hey, but somebody has already done it. So now, somebody was already there. It's what?
If two brackets, state equal to element.
So what?
Element, you have to be.
Master, so why are you looking on the way?
I don't want to look on it.
Hey, hey, let's go. Zero, yeah. Master. So something like this, right, also works. Now, there was another thing here is that you can just use this statement just like this. And if else statement must occur in an always block. So always at something like star, begin, and then end. So something like this also works. So you have to now take off all of this one, you put this one there. And then again, for the queue here, in case I use the queue inside the always block, I must declare it as a register before I use it inside the always block. Anybody else here? There is no switch statement in Verilog. States everywhere. There is no switch states. Can I use just one logic gate to do this?
One logic key.
And gate. How will it work?
You need a condition.
Yeah, we have two variables, we are comparing them. We are comparing state to a fixed value. Which is x0, right?
You need something like a selector equals key. Say multiplier. That's a multiplier.
What if I use an AND gate? Will it work? Will this work? The state is 2 bits, right? So stage 0, then stage 1. Then I have a NOT gate here, right? So if stage 0 here is 0, 0, probably say this is 1, 1, and then this will be 1. If stage here is 1, so 1, 0, any one of them will be 0. So yes, I've actually implemented it with just one gate, and then a NOT. You see how easy that is? Just think small. So you can do this in like 30 ways.
I finished marking your ways. If I'm working,
Okay, so the last one, but if you come here, there is wrong pound, there is minus one.
So what did I
Think about it. It's this one.
I just
Somebody has done.
then you didn't bring the beginner else.
Like for the airport,
I didn't bring the beginning. It's like I could not add the book. I mean, I wrote it from my mind, the one. Another one.
Alright, so we are all here, right? We are all here. How many are you here? Please count yourself, let me see. And then let me compare it.
Stay to the end.
29. But then, so, and then this is the whole thing. You can go and look at it. This is the whole thing without the done. That will execute this two things. So we are done. You can go.
I'm not. Check plus and plus 10.
Stop recording.